Hi, hello everyone. Thanks a lot for joining us either in person here or on Zoom for Marilena Loverde's talk. So Marilena started on the West Coast in her undergrad in Berkeley and moved to the East Coast from PhD at Columbia. And then after postdocs at the IES and University of Chicago, joined the YITP, the Chatziioannou Institute for Theoretical Physics of Stony Brook at Long Island as an assistant professor. And as of 3-4 months ago, she has rejoined us in the West Coast as an associate professor at the University of Washington in Seattle. And today we'll be hearing about neutrino dark radiation. So please take it away.
Okay, thank you. Thanks for the invitation. I always enjoy visiting Caltech and hearing about so many interesting things that people are doing here. Let me, actually, I forgot to hide this control. Oh. There we go. And it's also nice to get a little bit of sun and heat during the Seattle February. So today I'm going to tell you about learning about neutrinos or other sources of dark radiation from cosmic data sets. And let me start by explaining why this is something that I would want to do. And here's my motivational diagram. So as we know, the universe is expanding, and as it expands, it cools and it dilutes. And here's a cartoon showing temperature of matter in the universe, by which I mostly mean the photons, as a function of time. And it's decreasing roughly as for most of the time as 1/A, with little changes due to changes in the phases of matter at earlier epochs. Here we are today, where the cosmic microwave background photon temperature is about 10⁻⁴ eV. We know it was hotter in the past, and we know that when we heat up different types of matter, then the phases of things change. And when the temperature is high enough, then particles can be produced and interact that would not otherwise interact and be produced at low temperatures and energies. So for instance, when the temperature of the universe reaches the rest mass of electrons and positrons, then large numbers of electron-positron pairs are produced and are in thermal equilibrium with all of the other standard model particles. At temperatures of order in MeV, neutrinos are standard model neutrinos are the temperatures and densities are high enough that neutrinos are scattering frequently off of all of the other particles. And if you reach temperatures of order 100 GeV, then all standard model particles that we know about are abundant and scattering and in thermal equilibrium with each other. Now, the question is, if temperatures and densities are high enough, then there may be other particles that are also produced and are in equilibrium with the standard model at earlier times. So for instance, any other particles that are light enough, even if they're very weakly coupled to the standard model, might be produced and be in equilibrium with the standard model at very, very high energies and temperatures. For the microphone? Okay. Okay, let me know again if there's a problem. What is I find very exciting is that even tiny amounts of other particles that are produced in the early universe, should they remain stable for long epochs of cosmic history, we can detect them with current and future data sets. So the data sets that we can use are things like maps of the cosmic microwave background. So this is a Planck's all-sky map of the temperature anisotropies in the cosmic microwave background. And we analyze this by doing a Fourier transform and taking 2-point statistics or higher order correlation functions to look at data like the temperature power spectrum of this map. What has been the big change in microwave background data in the past decade and will be going forward in the future is that we now have increasingly precise maps of also the polarization of the cosmic microwave background photons. And we can decompose that polarization into things we call E modes and B modes, just according to the pattern that these polarization vectors make on the sky, and analyze these power spectra as well to look for stuff in the early universe. So specifically, very broadly, as I'll discuss a little bit more later, these are statistics on maps of the universe at much earlier time than today. And these maps clearly have features, scale-dependent features, such as these wiggles and damping scales. And those scales depend on physical properties of the stuff that was around at earlier times. And so we can use this data to learn about both, as I will talk about in this talk, we can use this data to learn about both the amount of relativistic particles that were present at earlier epochs, and we can also use this data to learn whether, learn some properties of any relativistic particles that were present. And just to motivate this, so you are probably familiar with these pie charts, which show the energy budget of the universe today, which is mostly dark matter and dark energy. But at the times that these cosmic microwave background photons are released, the energy budget of the universe is pretty different than today. While cold dark matter forms like the bulk of the energy density, there's really significant contributions from photons, microwave background photons, as well as relativistic neutrinos. So one hopes that you can, because neutrinos form a big component of the energy density at early times, we should be able to learn about them from these maps. This is an exciting time to be thinking about this because we're making really big advances in our ability to map out the cosmic microwave background temperature and particularly polarization. So this is a diagram illustrating that something like the change in the sensitivity of our maps with time. And there is this CMB stage 4 experiment, which I've been quite involved with, which is like a super experiment merging groups at the Atacama Desert in Chile with groups at the South Pole, and taking NSF telescopes and DOE, getting DOE involvement jointly to do really big cosmic microwave background science. And the key target, there's a bunch of different targets of this, but two of the big ones for this experiment are searching for new light particles and achieving a cosmological detection of the neutrino mass. These are also two things I've been involved in. I co-lead the maps to power spectra to parameters working group for this experiment. And our primary goal is this new light particles piece. Okay, so anything that was produced in the early universe, if it's stable and survives, is also going to contribute to the matter density today. So even those neutrinos that I discussed are still around. And because neutrinos are still around, we think, that means that the dark matter in our universe already has at least two constituents. There's something like cold dark matter, which has small velocities and therefore clumps very easily under the force of gravity and can form this backbone of the cosmic web that sieves structure and allows us to live in things like galaxies. In addition to that, there's another type of dark matter, which is hot dark matter in the form of relic neutrinos. It contributes probably a very small amount to the energy budget. We haven't yet detected the contribution of the neutrino dark matter to the energy budget of the universe with high significance at late times when they're non-relativistic. But there's a huge number of neutrinos. These are the second most abundant particles that we know about in the universe. And so even though their masses are very, very tiny, there's a very large number of them. And so this is another thing that is present in our picture of stuff in the universe today. And that's another piece of data that we'll use is taking maps of the distribution of galaxies and the distribution of matter. And we look at power spectra and correlation functions of these maps. This is a compilation of a bunch of data, including here cosmic microwave background as well, through data from galaxy surveys here. And this is one of the diagnostic tools that we can use to learn about the presence of relativistic particles as well. Okay, and we have huge amounts of data from galaxy surveys that are recently completed or ongoing and coming up in the next decade. So this is a fun time to be thinking about these things. Okay, so the outline of the rest of my talk is I'm going to present a thermal history of our universe, focusing on neutrinos or other contributions to radiation, meaning relativistic particles that could have been produced in the hot Big Bang. And the questions I'm interested in are, how much of that stuff is there? And what kind of stuff is there? Are there things that we can learn about neutrinos or other relativistic particles produced in the early universe that could be used to help diagnose what they are? Given that that stuff could be there and could have some properties that we can detect, I will talk about what the physical signatures of neutrinos or other hot relic particles are in the cosmic microwave background, large scale structure, and a little bit on gravitational waves. Okay, let's begin with the thermal history of the universe. Now, keep in mind, for much of the purposes of this talk, I can focus on neutrinos, and there's some things that I'll talk about that care that I'm talking about neutrinos. So because I'm talking about neutrinos, we have lower bounds on their mass. We know we know how neutrinos self-interact within the standard model and how neutrinos interact with other standard model particles. But much of the physical signatures that we'll see are just gravitational effects of neutrinos. So any other, the framework that we use to talk about relic neutrinos in the universe can be used to talk about other light particles that could have been produced in the hot Big Bang and exist today. So keep in mind when you see neutrinos that for much of the discussion, what I will say will also apply to some other new stuff. Okay, here is a thermal timeline of the temperature of the universe, which decreases with time. And along with that, I've given the scale factor of the universe, which gives the relative distance between objects compared to their relative distance today. And now I'm going to put a timeline illustrating some important epochs that have happened in the history of the universe. So here we are today when things are very cold. When the universe was when the temperature of photons in our universe was a few tenths of an eV, then one no longer had neutral hydrogen atoms, but there was enough photons around with sufficient energy to ionize hydrogen. So I had this plasma of photons interacting with protons and electrons and other light nuclei. At higher temperatures, from hundreds of keV through MeV, I would no longer have bound nuclei, but free neutrons and protons. At not much higher temperatures, but nearly higher temperatures, I would have sufficient energy in photons to pair produce electrons and positrons. And so the energy of the universe, the relativistic particles, would consist of photons and electrons and positron pairs. And then at sufficiently high energies, also nearby, all around the MeV scale, one would also have neutrinos scattering frequently off of all of this other stuff. So this transition here, when neutrinos go from being in thermal equilibrium and scattering frequently to when neutrinos stop scattering off of all of the other stuff, is illustrated by this cartoon, where these are the neutrinos down here that are just traveling on their own, separate from the photons and electrons and so on. And this is what we would call standard neutrino decoupling, this transition. The neutrinos that are released at this point then just travel through the universe, not scattering much off of anything else while they do so, much like the cosmic microwave background photons, which are released at the time of shortly after hydrogen recombination, travel uninterrupted through the universe to reach us today. So in addition to the cosmic microwave background, there is this cosmic neutrino background as well. Now, again, one could, if I have another light particle that could have been in equilibrium with the standard model at some early time, I would have another contribution of some mysterious stuff, which might have been part of this like hot soup of primordial stuff at early times that then decouples and then just travels freely to us today. Yeah.
This part is just for the left-handed components, the rights are then separate from other.
This should be left-handed neutrinos and right-handed antineutrinos. Yeah, just the standard model ones. Does that?
Well, the minimal standard model has massless neutrinos.
That's right.
left-hand. So they can get mass by adding also right-handed.
But sorry, right-handed antineutrinos as well, right?
Okay, right-handed.
So yeah, the ones I'm talking about here are just the light, just the light ones. No heavy right-handed neutrinos. Okay, so having illustrated those different phases, now I'm going to give some plots of some pie charts of the energy budget of the universe through time. So here we are today with dark energy, dark matter, protons and neutrons, blah, blah, blah. This is the time of the CMB that I showed earlier. Because different types of matter dilute differently, the relativistic stuff makes up a much bigger fraction of the pie chart, as does the cold dark matter relative to the dark energy. And at even earlier times, the relativistic stuff, neutrinos and photons, completely dominates the energy density. But as I go to sufficiently high temperatures, relativistic stuff is no longer just photons and neutrinos. I also have other things like electron-positron pairs that can be produced. And as I go to super high temperatures, I can have not just electrons and positrons, but other leptons, quarks, and so on that are all in thermal equilibrium. So what you'll notice here is that as the universe cools and this other stuff can no longer be in thermal equilibrium, where does that stuff go? Well, things in the other leptons that don't that are heavier, for instance, annihilate, and that energy will go into heating the other stuff that is left. So for instance, between this part of this epoch here with this pie chart, I have these E plus E minus pairs, and over here, they're gone, and the energy from these went into the photons. It went into heating the photons, but not the neutrinos. And so that's why photons take up a bigger part of this pie chart. So the idea of looking for neutrinos or other particles is that we can ask questions like, if there's some other mystery stuff that was present at some early time, it might have contributed to the energy budget in some significant amount. We can't probe these epochs, but that stuff could persist in some tiny sliver of our pie chart today, even at CMB times, which we might be able to detect. And we should go look for it. Okay. So the one type of radiation that we can detect really well is the cosmic microwave background photons, and those can be measured today. And they have a temperature that we measure, and the distribution function of their momentum is also measured, and it looks like a Bose-Einstein distribution with this temperature. From this, one can predict what the temperature of the relic neutrino background should be, and it's about 2 Kelvin, and it would have a relativistic Fermi-Dirac distribution. The photons are a little bit hotter than the neutrinos because they were heated by electron-positron annihilation after the neutrinos decoupled from everything else. So at this, when these E plus E minus pairs disappear, that energy goes to the photons, but the neutrinos don't get any of it because they're no longer interacting with the standard model, or roughly. And I could have some other new mystery stuff, which could have been produced in the early universe. We haven't seen it, so it must have a temperature which is much lower than both photon and neutrino temperatures. And that could happen if the other stuff decoupled prior to other transitions in the type of matter that are present in our universe. For instance, prior to annihilation of other leptons or prior to the QCD phase transition. But if the stuff was once in thermal equilibrium, it would also inherit a relativistic Fermi-Dirac or Bose-Einstein distribution. And then this quantity, the temperature, if we knew it, predicts both the number density, the energy density, and it completely. If those particles become non-relativistic at late times, and we know the number density, but we don't know the mass. So that would be something else that we could look for in cosmic surveys. So to put some numbers to this, Today, the cosmic neutrino background, the prediction of a relic neutrino C with a temperature of about 2 Kelvin predicts that there's about 330 neutrinos per cubic centimeter. So it's 50 per 50 per neutrino state with one-handedness. And we have only upper bounds on the energy density, and that's less than about 11 eV per centimeter cubed. You can compare this with the cosmic microwave background, which we can measure directly through, with antennas. And there, the number density of CMB photons is about 400 per cubic centimeter. And today, the energy density is much smaller because photons have no mass. So if I have some other particle that was in equilibrium with a standard model at some temperature, at high temperatures, but then it ceases to interact with the standard model at a particular temperature, we'll call T freeze, its interactions freeze out, then I can predict the temperature of that other new mystery stuff in terms of the temperature of the standard model stuff, with the standard model photons and neutrinos going through this exact same exercise. If I have this other stuff that's produced in the early universe, at high temp, it at one point had a common temperature with the photons in our universe, then it decoupled, it travels to us on its own, but the other stuff will have a temperature which could be increased through injections of energy from annihilations of electrons and positrons, or from the QTD phase transition, or the other standard model particles falling out of equilibrium. So if I know the temperature something freezes out at, and I know its degrees of freedom, then you can get a firm prediction for what the relic energy density and that stuff would be. And the way that cosmologists quantify this is you can compute the relic energy density, and they write it as this parameter n effective, which means that they're measuring it in units of the predicted energy density for one neutrino state, one neutrino and anti-neutrino state. So if delta n effective is 1, then it's something that also has a temperature of 2 Kelvin and is therefore present today at about 100 per cubic centimeter. But for things that decoupled earlier, their energy density is lower because they did not receive the energy injection that all the standard model stuff did. And so that is what this plot is illustrating here. And what I like about this very much is that as you go to, if there's this asymptotic value, if I have a single real scalar, which is the minimum thing I could have that was ever in equilibrium with the standard model and was light, there is a firm prediction for what that will contribute to the energy budget of the universe at early times. And that is that this n effective parameter is 0.027. So it's about 3% of the energy density of a single neutrino state. If I have more than one thing, or some particle with more degrees of freedom than a real scalar, then I will get larger contributions to the energy budget. Okay, so the takeaway from that part is that relatively simple assumptions, asking if I have some particle, which is light or massless, that ever interact with the standard model, then I get a threshold for how much that contributes to the energy of the universe. So how do we detect this? At times probed by the cosmic microwave background, the energy density is probably mostly just photons and neutrinos. So let me first tell you how we detect the energy density in relativistic neutrinos in the early universe. Is that we use measurements of the radiation density given to us by the cosmic microwave background. The reason we can infer the radiation density from the cosmic microwave background is that Einstein's equations relate the expansion rate of the universe to the energy of the matter that's present at early times. So the expansion rate is some physical quantity that's going to dictate things like scattering rates that are relevant. So let me show one illustration of that. So this is the cosmic microwave background power spectrum, which has these wiggles, the acoustic peaks, but there's also an overall damping here. of the perturbation. So the anisotropies in the microwave background are washed out by the finite distance that photons travel between scattering off of electrons. And that distance scale is just determined by the expansion rate. So the number of scatters that photons have depends on like the Thomson cross-section and the expansion rate at that time. So the overall damping here is a probe of the expansion rate at early times, which is therefore a probe of the total radiation density that's present. We have direct measurements of the photon density, and we have predictions for the neutrino density. So you can check whether these measurements of the radiation density that come from a microwave background are in agreement with what we predict. And they're in striking agreement. So the standard cosmological model would predict that the radiation density of the universe at times probed by the microwave background is 60% photons and 40% neutrinos. And that's in complete agreement here. So let me show you exactly how good the agreement is. So the Planck 2018 data from CMB plus some late time data gives constraints on the effective number of neutrinos to be 2.99 plus or minus about 0.3. So that's a 10% detection of the expected amount of neutrinos in the very early universe. So we have absolutely detected, it seems very much like we have absolutely detected the presence of relic neutrinos at early times when they were relativistic. And we hope to get constraints that are of order instead of 0.3, something like 0.03, 0.04. And that will allow us to get much more precise constraints on the amount of stuff that's present. So there's not much room for additional particles, but they could be there. And that's something that we will continue to look for. Just pause for questions. So suppose these measurements detect some extra contribution to the energy budget in the universe. Well, all we're doing is gravitational measurements, so we don't know anything. All we know is that there's extra energy there, but we don't, since we're not measuring it directly, we don't know anything about how that extra energy, interacts with the standard model or not. And so one thing that you can do is ask if there are other properties of that extra radiation that you could learn about. And so let me just point out, when people talk about looking for contributions to ineffective or extra relativistic particles in the early universe, there's all kinds of things that people look for. So even gravitational waves would act like dark radiation from the presence of the early universe, like some huge amount of gravitational waves produced for some reason could contribute enough to the energy budget in principle that you could detect it. And you could have sterile neutrinos, you could have light axions, or all kinds of things people think about. So one way that we can get another handle on what this stuff is by looking at the gravitational dynamics of the perturbations. Again, I'm going to start with the test case of neutrinos and compare neutrinos to photons at CMB times. So neutrinos decouple from their interactions with themselves and with the standard model at very early times. So at redshifts of about 1 billion or times of order 1 second in the history of our universe. So that means if I take a blob of neutrinos in the early universe, I have some overdensity of neutrinos, here they are, and I watch what happens to that, they all just free stream out. And this blob will expand at the speed of light, because that's the speed that these neutrinos are moving at. This is distinct from something like photons at times probed by the CMB. The photons are scattering a lot, not off of each other, but off electrons and protons that are present. And so if I look at the photons, because they are so tightly coupled to other stuff, we don't treat them as a gas of freely moving photons, but as a tightly coupled photon baryon fluid. And this stuff as a fluid behaves differently than this other gas of free streaming particles over here. In particular, the perturbations in the photon baryon fluid propagate at a speed which is smaller than the speed of light. It's 1/√3 times the speed of light because of all of this tight coupling. And so this distinction in how perturbations evolve in free streaming neutrinos compared to how perturbations evolve in photons, leads to some distinct signatures in cosmic microwave background and large-scale structure data. So the physical effect is that the perturbations travel at a different sound speed. And moreover, while this photon baryon fluid stuff can be described as to good approximation as just a perfect relativistic fluid with a sound speed, the neutrino distribution is much more complicated. It doesn't look like a fluid at all. It has anisotropic stress, and I need the full phase space distribution or all the moments in the Boltzmann hierarchy to describe this stuff. And that leads to distinct physical effects on the observables. So let's look at this. Here's a diagram illustrating what a neutrino might see in terms of, or how I might quantify how much the neutrino is interacting with stuff. So suppose I modify neutrinos so that instead of decoupling when we expect standard model neutrinos to decouple at temperatures of an MeV and redshifts of 1 billion, I allow them to have some additional self-interaction. Then the neutrinos will see the universe at late times today. They may have decoupled from this interaction, and so the opacity is 0. So when the opacity is 0, they're just free streaming. At early times, when the opacity is 1, then they're very, very tightly interacting, and they're acting much more like the photon baryon fluid. So depending on, and this transition could happen at some variety of times, but it will be some gradual shape like this orange curve here, or somewhat gradual transition like this orange curve. Here I've illustrated this to happen at a redshift of 10,000, but the shape is pretty similar no matter which where you move this curve back and forth. If I want to look at all kinds of different things, some other dark radiation that might exist in our universe, for instance, ask whether there's dark photons that exist in some dark sector, then I could also have, there are examples of beyond the standard model physics where you propose these additional copies of the standard model with dark photons interacting with dark electrons and dark protons and so on, but have different binding energies and therefore would form their own dark hydrogen atoms and so on at different epochs. That type of dark radiation could also be detected gravitationally. And we could also see that type of dark radiation going through some dark recombination. And that transition would happen much more sharply, which is illustrated, or could happen much more sharply, shown in this green curve. So from the perspective of the observables we're looking at, the point is that allowing neutrinos, looking at neutrinos or other sources of relativistic particles, I can have qualitatively two qualitatively different regimes. One, when they interact a lot on this right-hand side of the plot, and they're fluid-like, and one where they don't interact very much at all, and they're free streaming on this side of the plot. That transition is something that is time dependent, and that will lead to time dependent changes in the evolution of things that determine our observables. For instance, the gravitational potentials in our universe, which give rise to the anisotropies in the temperature and polarization data. So these time-dependent changes in these things will lead to scale-dependent changes in our observables here. So here's an illustration of this. And these two plots show the power spectrum of the E-mode polarization. And in both plots, I show the effect of changing the amount of relativistic particles in the early universe. So the black curve looks like the standard model, and the blue and red curves, I add energy and relativistic particles in the early universe in units of like 1 neutrino species, keeping things fixed like the matter radiation equality time and the horizon scale. The reason that the left plot looks different than the right, so the left and the right plot have the same cosmology, the same amounts of relativistic particles. The red curve over here has the exact same amount of relativistic particles as the red curve over here, but they look different because on this side I've added particles which are fluid-like, and on this side I've added particles which are free streaming, like standard model neutrinos. And so that leads to distinct scale-dependent changes in the power spectra that one could detect. So the key takeaway is that I have the same extra radiation, but I have it composed of different types of particles, and I can see it. I think this should be an animation. There we go. So this plot is combining those ideas and showing what the power spectrum of E-mode polarization looks like, comparing things that are fluid-like or free streaming, like standard model neutrinos in red, versus something that transitions from being fluid-like to free streaming at some finite time. So the black curve is changing from something that is fluid-like that starts free streaming at very, very early times and therefore looks a lot more like the neutrinos, to something that decouples at very, very late times and looks like something which is just a pure fluid. So that's something we can go look for. Something else that is cool is that the data, or these observables anyways, this is not something we've measured, this is just a prediction, can tell not only whether something transitions from fluid-like to free streaming. So here, if I measure these curves, I could identify not only that there's extra radiation, but that it had some transition in its behavior at a finite time. But some of the observables are also even sensitive to the width of that transition. So on this plot, I'm showing the fractional change in the matter power spectrum, one of our observables, comparing the fractional change in the matter power spectrum for a universe where there is half of a unit of extra energy density in units of relativistic neutrinos that is either fluid-like forever, giving the yellow curve, or decouples at a finite time, here redshift of 100,000. And that decoupling could be decoupling from a simple model of decoupling from self-interactions, as in the solid curve, or an instantaneous decoupling, like I might expect for dark recombination, which is in this dashed curve. And that gives a distinct signature in the shape of this power spectrum. There are also examples of changes to neutrino physics where rather than decouple, I have interactions that recouple. So I imagine that I have neutrinos that are like standard model neutrinos and decouple from their own self-interactions and interactions with everything else, a redshift of 1 billion. But then there's some other stuff around that mediates a self-interaction that then recouples the neutrinos together at a late time. And that is what is illustrated here. And that also leads to distinct changes to the shapes of these observables. Okay, so given that this is something I'm claiming you could look at, it is natural to ask what current data says. So let's first look at the case where we pretend that we don't know much about neutrinos, and we want to ask whether CMB data prefers neutrinos that are indeed free streaming since redshift of 1 billion, like we expect from the standard model, or neutrinos that have some additional self-interactions. I'm going to present some analyses of current data. And this work was completely led by Thijs Brinkman, who was my former postdoc at Stony Brook, and Jae-Hook Chang, who was a Stony Brook student, but is now a postdoc at Maryland. So here's one example of the type of analysis we did. So on this plot, we look at Planck, temperature, polarization, power spectra, gravitational lensing. You can add BAO data. It doesn't make a big difference for what I'm about to say. And we look at joint constraints on the effective number of neutrinos here on this axis and the neutrino decoupling time. So this is the log of the neutrino decoupling time. So standard model neutrinos would decouple up here at like 9. And what we find is that this data can be fit well by two distinct examples of neutrinos. There's one case where the neutrinos, what you get is the usual number of around 3 neutrino species and a lower bound on the time at which they decouple. So the CMB data is not very sensitive to interactions that happened before redshift of about 10 to the 5. And so you just get a lower bound on the interactions. So this little blob down here is a standard model blob. I would expect standard model neutrinos to live somewhere up here, but the CMB just isn't that sensitive. So all that can say is for sure that they didn't continue interacting until later times. Except there's this little island over here where this data is also fit comparably well by a model of the universe where I have a little bit fewer neutrinos that are present, but they remain strongly interacting until relatively late time. So this little island also fits the data. And in this case, all the neutrinos that are present in our universe, all the relic neutrinos continue to interact until a redshift of 10,000. Or a times are different. So this is the CMB data can't probe interactions in neutrinos after prior to about 50 years. This little blob has the standard values of all the other cosmological parameters, omega matter, the distance to the CMB, and so on. This little blob has neutrinos continuing to interact until time of about 4,000 years after the Big Bang. And the cosmological parameters over here that fit the rest of the data are different. It gives little shifts to like the baryon density and the scalar spectral index and things like that. This mode, if you're a geek in cosmology or remotely interested, there's this H0 issue where the CMB data predicts a different value of the Hubble constant than is seen with low redshift measurements. And this second mode does not exist when you add Hubble constant data. So adding self-interacting neutrinos does not help with the Hubble tension. This is just some other mode that exists. Some of the parameters shift over here, but not the Hubble tension, not the Hubble constant. So there's no solution to the Hubble. There's been some talk about this, but there's no solution to the Hubble tension with this. But this mode is fun. And if I was just only cared about cosmology, I might be really excited about it, but it's just incompatible with particle physics data. And it's not like it's preferred over this. So it's ruled out. And there have been a handful of nice papers on this, but this is a plot from our paper that adapts constraints that are given in this paper by this Fermilab group here on constraints on the interaction, the self-interaction strength for neutrinos if it was mediated by a Meyer-on here. And so the only thing to point out on this curve is that these contours are, so suppose all standard model neutrinos are interacting via their mass eigenstates here on this green curve, then this entire region of these parameters is excluded. And the CMB mode we found lives way up here. So that's way outside of constraints from particle physics. If I wanted only 2 of the neutrino states to interact, or even only 1 neutrino state to self-interact, the constraints are weaker, like where this red curve is, but they would still only allow self-interactions that persist until, say, a redshift of 10 to the 6 or something. So this plot is basically saying that constraints from particle physics are probably stronger than constraints from cosmology on the self-interactions, because current cosmological constraints cannot probe interactions that persist, that cease by redshift of 1 million or something. I mean, this is about the limit of how well cosmology can do. But I could still ask the question of, well, suppose then that instead of forcing all neutrinos to self-interact, I allow only a fraction of the neutrinos to self-interact, or I ask the data if I can ask the CMB data, I can free up the fraction of neutrinos that self-interact and ask if what are the constraints on the fraction of the neutrino energy density that can have some scatterings. And so that is another exercise that we did. And the basic takeaway is there's no evidence for anything new or any non-standard neutrino interactions, but there's room for something to be detected in the future. So this plot illustrates the constraints on the total energy density and relativistic particles and effective, and the fraction of that that is interacting. So you're roughly allowed to add, you can have roughly the standard amount of relic neutrinos, and you can let 25% of them be self-interacting, and that's a good fate for the data. And you get no real preference for the time at which those interactions would exist. You could have self-interactions which exist at really high redshift, which maps onto the standard model, or at very, very low redshift, and we just wouldn't see much of them. Okay, so I would say there's no compelling evidence for new neutrino interactions, but it's a good exercise. We should use the data to check on this, because neutrinos, astronomical data sets have provided surprises about neutrinos in the past, and so we should continue to use them to test the standard model. But I could also suppose that neutrinos are just standard model neutrinos and ask whether there's any extra contributions to the radiation density from some of these exotic scenarios, and whether the constraints on that extra radiation density weaken if I allow it to self-interact. So this is a current project and then ongoing work with these same characters, and also with help from Peji Du, who's another Stony Brook postdoc about to head to Rutgers. So here in this exercise, we look at constraints on new particles that could decouple from self-interactions, that could decouple from something like dark recombination, which would lead to a sharper transition in their interactions, or could even recouple. And the takeaway is we use the same current CMB data. We look for all this stuff. Unsurprisingly, we find no new physics, but the data does allow room for there to be a little bit more dark radiation if that dark radiation has some self-interaction. So that's illustrated. These are busy plots, but the black squares highlight the part of these which shows how much extra radiation there is, depending on how strongly it self-interacts. And in all these cases, when the self-interactions are a little bit stronger or present for more of the CMB history, you're allowed to have a little bit more dark radiation. Nothing has been detected, but this demonstrates the power of these experiments to look for new physics. And this is something that we'll continue to do, in particular with the CMB stage 4 experiment. So one can ask, suppose we detect an extra contribution to the radiation density that's like 10% of one neutrino. How accurately can we measure the time at which it decouples? And the answer is, well, not that accurately, but at the tens of percent level, you could measure that. And that would tell you something about, could tell you something about the type of interaction that was taking place. Okay, in the last few minutes, I'll tell you about one more example that's quite futuristic, but it's fun to think about. So the CMB data is probing the history of the universe and the types of matter that are in it, roughly from redshifts of 1 million until today. It doesn't seem easy to learn about anything that's happening at much earlier times. And even at redshifts of 1 million, we're not very sensitive to things like whether the types of matter that are around are tightly coupled or free streaming. So one could ask, how can I probe interactions at an earlier epoch? So in particular, I think it would be super cool if you could find some observable that allowed you to detect standard model neutrino decoupling. I might not learn anything new, but that would be like a remarkable demonstration of the synergy between particle physics and cosmology. And so in thinking about this, one thing that is helpful to know is something that was pointed out by Weinberg in 2004, which is that the presence of free streaming particles affects the propagation of gravitational waves. And only gravitational waves on very, very large scale. So gravitational waves with cosmological scale wavelengths. That shorter scale gravitational waves that are seen from black hole binaries, unfortunately, are are just not sensitive to the types of matter, to whether free streaming particles are present in the universe or not. But very, very large scale gravitational waves, such as those that are produced after inflation, or could be produced in some phase transitions in the early universe, do behave differently in the presence of free streaming particles that source some anisotropic stress. So with my current postdoc, Zach Weiner at the University of Washington, we've been exploring this in more detail. And let me illustrate this. So suppose I had some primordial gravitational waves. The amplitude of these is damped significantly if a lot of the radiation is free streaming, and it's damped not at all relative to the case where there's no free streaming radiation, if there's no free streaming radiation. So one can ask, suppose that I have some detection of primordial gravitational waves. So primordial gravitational waves with a tensor to scalar amplitude of like 0.05 would give a contribution to the energy density, which is given by this black dashed curve here. So this shows the energy density in gravitational waves per frequency or per Fourier mode K. Now, different Fourier modes are probing different epochs in the history of the universe. So Zach made this nice plot that combines the frequency of the gravitational waves down here in F compared to their wavelength or their wave number K, which is easy to convert, but also shows what temperature, what was the temperature of the universe that is probed by gravitational waves of this frequency, or at what epochs in redshift in cosmological history am I learning about by measuring gravitational waves at different frequencies. So the black dashed curve is the spectrum of primordial gravitational waves that I would expect from inflation. The amplitude of that black dashed curve is, of course, completely unknown. So this is showing something just at the current limits. But what I want to illustrate is that this is the prediction for a simple inflationary model would be this black dashed curve. And it has a couple of features in it. It has a few features that change depending on that are related to these changes in the amount of degrees of freedom that are in equilibrium. But it has this big dip right here. And this dip is due to the decoupling of standard model neutrinos. So once standard model neutrinos decouple, the gravitational waves are damped. So the gravitational waves at these frequencies entered the horizon after neutrinos had decoupled from their self-interactions and were therefore damped. If I changed neutrinos so that they decoupled from their self-interactions later, then I would get the yellow curve, going to these green curves, going to these blue curves. So this purple curve shows what the gravitational waves would look like if neutrinos had never decoupled at all. And that would make them that would make the gravitational wave amplitude larger by like 30%. So if one could probe gravitational waves, primordial gravitational waves at a number of these epochs, then one could detect this transition here, which would be a signature of standard model neutrino decoupling. That looks hopelessly out of reach for proposals that people have discussed. These are current CMB constraints. This should get better and get into this region, but reaching the standard model decoupling just is way far away from pulsar timing and direct measurements that have been proposed, but who knows. Also, if there were causal gravitational waves that were produced from like phase transitions or something, the neutrino damping also affects them. And the particular changes to the power spectrum depend on the time at which those gravitational waves were produced and so on. So wrapping up, future CMB experiments are reaching exciting thresholds for detecting new particles. And in particular, we are looking at constraints on the effective number of degrees of freedom that are pushing us, the better we measure this, or the more precisely we can measure this, the earlier in the history of the universe we are probing. So that is, we're probing what degrees of freedom were present at higher and higher temperatures. And this is where we expect to be with the CMB stage 4 experiment. Large scale structure data Also will provide interesting constraints, has already been shown to provide some constraints on the abundance of relativistic particles. There's very little work done, but more and more happening on signatures of relativistic particles in large scale structure data and signatures of their interactions. And of course, in gravitational waves, as I mentioned. So in summary, cosmology provides interesting information. A variety of data sets can tell us something about the energy density and the interactions. And at present, we don't find anything, but opportunities exist for future detection. And this could have interplay with other examples in particle physics, which predict additional light relics. So, thanks.
Start, maybe some questions from the room. Zoom as well.
Yeah, you mentioned this at the very end, but so phase transitions in the early universe also can give you a gravitational wave. That sounds like
Mhm.
and I guess it's still faster.
Yeah.
Background. Is there, so let's say the discovery is made by CNBS4. Do we know which one it is? Or?
I think it depends.
You want me to repeat that?
Oh, that's right. Sorry, thanks. So the question was, there are other sources of gravitational waves, such as stochastic backgrounds from phase transitions or something. If CNB detects something here, do we know whether it's primordial, whether it's from inflation or whether it's from some causal process at later times? And I think, I think if CNBS4 detects gravitational waves, the first thing that they'll be doing is fitting for a prediction for a scale invariant primordial spectrum. And if it fits that well, I expect that most people will conclude that those are indeed inflationary gravitational waves. There will be holdouts who are skeptics of inflation altogether, but with CNBS4 alone, one will not be able to measure, given the current constraints on the amplitude of the gravitational waves, it will be hard to detect the spectral index. And inflation, as I'm sure you know, there's this consistency relation between the amplitude of the spectral index, the tensor spectral index, and the amplitude of the gravitational waves that could really convince you that that's what you're seeing, but I don't think we'll be able to reach that. So, yeah. Does that answer your question?
Kind of. If you could verify that relation, it would be
Yeah,
strong evidence.
I think so, yeah. Question.
In this check, do you use the decoupling time to calculate the temperature?
Good. So the question was that I said that there are 3 neutrino species that are consistent with the data, and do we use the decoupling time or temperature to make that calculation? And the answer is sort of. The temperature, let me see if I can find a right plot to illustrate this. Yeah. So the precise thing to say is that the CNB data is consistent with detecting there are constraints on the radiation density of the early universe from the CNB, which are consistent with the expected energy from 3 relativistic neutrinos here. And that means both, so that's a measurement of the energy density is some combination of the number of neutrino states and their temperature. And the prediction for the temperature the prediction for their contribution to the energy density is flat as long as they decoupled somewhere in this region, let's say. See this, so neutrinos would be this red curve, the wild fermion, that decouples at temperatures here. So it's around an MeV here. And so as long as they decoupled anywhere in there, you get the same contribution to the energy budget. It's only if they decoupled earlier that you would get a different prediction.
So you only need the number of particle types of the decoupling.
That's right. Yeah. Yeah, precisely.
One question in the chat when you read it. From Ken Hyman, how do streaming neutrinos down the gravitational waves propagation? Is it by changing the potential in large scales?
Yeah, so that's a good question. So okay, so as Chen knows, the scalar vector and tensor perturbations at linear order are decoupled. So it's not the potential that changes on large scales, but it's that the neutrino the neutrino distribution function can source tensor perturbation or can couple to tensor perturbations. So there is, when I look at, indeed, the Newtonian potentials like phi and psi are changed, but also the evolution equation for the gravitational waves has acquires some source term that depends on the tensor piece of the perturbation to the neutrino distribution function. And that is what affects the evolution of gravitational waves. Does that answer your question, Chen?
She said, yes, it does.
Any other questions? No, let's thank Marilena again.
Thanks.
There's a couple more open slots in her schedule tomorrow, so let me and Marilena know. And with that, thank you for joining us.
Thanks.